Have you ever just, stopped and looked up
Mm.
and seen one of those massive planes just sort of hanging there in the sky?
Yeah, these enormous metal machines, way heavier than air.
Exactly. And somehow they just soar, looking almost effortless. It seems to defy, well, everything.
It really does.
Today, we're diving deep into the fundamental principles that make that possible. How does it actually work?
It's fascinating stuff, and for this deep dive, we've pulled together some really great sources. We're looking at excerpts from detailed aviation handbooks.
The real technical manuals.
Right, the ones that break down the physical laws, the aerodynamics, how aircraft maneuver, all the nitty-gritty details.
Okay, so our mission today is to unpack these natural forces acting on a plane. Understand how they interact. It's like this constant dance, right?
That dynamic dance, definitely.
And reveal the surprising things pilots need to master. Prepare for some moments because we're going to try and demystify how these giants stay up there.
Sounds good. And to really get flight, we have to start with the basics, the invisible foundation it all relies on, the air itself.
Right, air. We breathe it, but we don't often think of it as substantial.
But it absolutely is. People think of fluids as liquids, water.
Yeah.
But air, it's mostly nitrogen and oxygen. Other gases mixed in it is a fluid.
Okay.
It has mass, it has weight, and just like water, it flows, it takes the shape of its container.
So it's like we're flying through a really thin, invisible ocean.
Mm-hmm.
That still feels a bit weird to say.
In a way, yeah. Gases are much less dense than liquids, obviously, but they share that key property. They flow, and that flow introduces something critical.
Viscosity.
Viscosity. Okay, sounds technical. What does it mean for a plane moving through air?
It's basically a fluid's resistance to flowing. Simple example. Pour honey, then pour water.
Honey flows slow, water flows fast.
Right. Honey has high viscosity. Air has very low viscosity. It flows super easily.
Yep.
But it still has this subtle stickiness. It resists things moving through it. And that stickiness, that leads to friction, doesn't it? Because the air is rubbing against the plane's surface.
Precisely. Friction is just that resistance when two surfaces move against each other. Even a super smooth airplane wing, microscopically, it's rough. So as air flows over it, some air molecules literally stick to that surface. Friction holds them there.
So that's the boundary layer people talk about, this thin layer of air almost stuck to the wing.
Exactly. Like the wing is dragging a tiny invisible blanket of air along with it.
Okay.
And once that boundary layer sticks because of friction, the air's own tendency to stick to itself, that's the viscosity part, causes even more resistance further out.
Right.
So you combine that friction at the surface and the air's internal stickiness, viscosity, that combined resistance to airflow over the wing. That's what we call drag.
Got it. So the simple act of moving through the air creates resistance. Okay, let's shift to another invisible force, atmospheric pressure. This is huge for flight, not just weather forecasting.
Absolutely not just weather. Pressure, fundamentally, is force applied perpendicular to a surface.
Yeah.
Like the air pushing on your skin right now.
We feel it all the time, but don't notice it.
Right. And anything immersed in a fluid like a plane in the atmosphere feels this pressure evenly all around its surface.
And air has mass, gravity pulls on it, so it has weight. And that's what creates the pressure.
That's the source. Air exerts pressure equally in all directions, and it's significant. At sea level, standard conditions, it's about 14.7 pounds pushing on every single square inch of surface.
14.7 CSI. Wow.
But here's the kicker. It drops off fast with altitude, go up to 18,000 feet, and the pressure is literally cut in half.
Half. That's a massive difference.
Yeah.
So how do pilots deal with this constantly changing pressure? It must affect everything.
It does. That's why we use a reference, a standard atmosphere. It's a theoretical model. It sets a baseline.
Yeah.
Sea level temperature is 59 degrees Fahrenheit or 15 Celsius. And sea level pressure is 29.92 inches of mercury, or 1,013.2 millibars. And then it defines standard lapse rates, how temperature and pressure typically decrease as you go up.
Lapse rates, like how much it cools per 1,000 feet.
Exactly. Temperature drops about 3.5 degrees Fahrenheit, or 2 Celsius per 1,000 feet, up to a certain altitude. Pressure drops about 1 inch of mercury per 1,000 feet initially. This International Standard Atmosphere, or ISA, gives everyone a common yardstick.
Okay, so that standard baseline lets us define pressure altitude. Is that just your height relative to that standard pressure level?
That's it. An aircraft's altimeter is basically a sensitive barometer. When you set it to that standard pressure, 29.92 inches of mercury, it shows your pressure altitude.
And why is that useful?
It's crucial for understanding aircraft performance, how the plane should perform based on that standard model. And it's used for assigning flight levels, especially higher up where everyone flies based on pressure altitude, not their actual height above sea level.
Okay, but then there's density altitude. That sounds like it might be even more important for how the plane actually flies on a given day.
It arguably is. Density altitude is the real performance killer or enhancer. It's the pressure altitude corrected for non-standard temperature.
Corrected for temperature, so a hot day is different from a cold day, even at the same pressure altitude.
Massively different. Density altitude tells you the altitude in the standard atmosphere where the air would have the same density as the air you're actually flying in right now.
Okay, break that down. Why does density matter so much?
Because less dense air, thinner air means less performance, period. The engine produces less power because there's less oxygen per cubic foot. The propeller gets less bite. And crucially, the wings generate less lift.
So less dense air means the plane performs worse.
Significantly worse. Longer takeoff rolls, slower climb rates, lower ceilings. It affects everything.
And what makes air less dense? High altitude is one.
High altitude, definitely. Lower atmospheric pressure.
Right.
High temperatures, warm air is less dense than cold air. And high humidity. This one surprises people.
Humidity. Wet air feels heavy. Shouldn't it be denser?
You'd think so, but water vapor molecules, H2O, are actually lighter than the nitrogen, N2, and oxygen, O2 molecules they displace in the air. So moist air is less dense than dry air.
Wow. So high humidity reduces performance too.
It does. It increases density altitude. The sources give a great example. At 8,000 feet elevation, on a hot day, 80 degrees F, with high humidity, 75 degrees dew point, the density altitude isn't 8,000 feet. It's over 11,500 feet.
That's huge. The plane performs as if it's nearly 3,500 feet higher than it actually is.
Exactly. It's a major factor pilots have to calculate, especially for takeoff from high-elevation airports on hot, humid days.
Okay, so the air itself is this incredibly dynamic, invisible medium. Understanding its properties, pressure, density, viscosity is step one.
It's the foundation.
Now let's get into the forces actually acting on the aircraft in that air. The big four: thrust, drag, lift, and weight.
The cornerstones of flight. Thrust is the forward force, usually from the engine and propeller or jet engine. It pushes or pulls the aircraft forward.
Opposing that is drag, the resistance we already talked about, pulling backward.
Correct. Then you have lift, the upward force, mainly generated by the wings, that opposes gravity.
And weight, the downward pull of gravity on everything: the plane, fuel, people, cargo.
Those are the four. And in steady flight, meaning constant speed, constant altitude, not accelerating, these forces are in equilibrium.
Equilibrium. Does that mean they're all equal?
Not necessarily equal to each other, no. It means the opposing forces balance out. The sum of the upward forces equals the sum of the downward forces, and the sum of the forward forces equals the sum of the backward forces. They cancel each other out.
So lift equals weight, and thrust equals drag in straight and level, unaccelerated flight.
That's the classic simple case, yes. If you're climbing or descending at a constant speed, it gets a bit more complex, with components of thrust and weight acting vertically or horizontally too. But the principle of equilibrium still holds. It's a constant balancing act.
Okay, let's zoom in on the star. Lift. The force that really seems magical, defying gravity. How do wings do that? Is it just pushing air down?
That's part of it, based on Newton's third law. For every action, there's an equal and opposite reaction. The wing is shaped and angled to deflect air downwards,
The action?
and the reaction is the air pushing the wing upwards. That's definitely a component of lift.
But not the whole story. I feel like there's more.
There is. The other key player is Bernoulli's principle.
Ah, Bernoulli. Pressure and speed.
Exactly. Bernoulli figured out that for a moving fluid, remember, air is a fluid. As its speed increases, its internal pressure decreases.
Faster flow, lower pressure.
Right. Think of a Venturi tube, that hourglass shape. Air speeds up in the narrow bit, and the pressure there drops.
Okay. How does that apply to a wing?
An aircraft wing, an airfoil, is specifically shaped, usually curved more on the top surface than the bottom.
The camber.
Yes, the camber. Because the top surface is more curved, the air flowing over the top has to travel a longer distance to meet up with the air flowing under the bottom in the same amount of time.
So it has to go faster over the top.
It has to speed up. And according to Bernoulli, faster airflow means
Lower pressure.
lower pressure on top of the wing compared to the higher pressure underneath. And that pressure difference creates an upward force. The higher pressure below pushes up, but more significantly, the lower pressure above pulls the wing upward.
So it's a push from below and a pull from above,
Yeah.
but the pull from the low pressure on top is actually the bigger contributor.
That's what the physics tells us, yes. The negative pressure, lower than atmospheric, on the top surface is typically responsible for the majority of the lift generated.
That's the aha moment. It's not just brute force pushing air down.
It's a sophisticated interaction with pressure. The airfoil shape, the leading edge, trailing edge, the chord line connecting them, the camber, it's all designed to maximize this pressure difference efficiently.
And different planes need different shapes, right? A slow cargo plane versus a supersonic jet.
Totally different airfoil designs, you optimize for different things. High lift for slow flight often means a deeply cambered wing, but that creates a lot of drag at high speeds. High-speed wings are often thinner or less cambered.
But modern jets seem to get the best of both worlds. They have those flaps that come out.
Exactly. That's the genius of high-lift devices. Trailing edge flaps, like Fowler flaps, extend backward and downward, increasing wing area and camber. Leading edge devices like slats or Kruger flaps extend from the front edge, also increasing camber and helping the air stick to the wing at higher angles of attack.
So they temporarily reshape the wing for takeoff and landing.
Precisely. They morph the wing into a high-lift configuration for slow flight, then retract for a clean, low-drag shape for cruise. It's brilliant engineering.
Okay, so the pressure isn't uniform across the wing, right? It changes depending on where you are on the surface and the angle the wing meets the air.
Right. The distribution of pressure varies, especially with the angle of attack, or AOA. That's the angle between the wing's chord line and the oncoming airflow, the relative wind.
Angle of attack, AOA. That sounds important.
It's fundamentally important. Changing AOA is the primary way a pilot controls lift. But where all that pressure effectively acts is also key. We call the average point the center of pressure, or CP.
The CP. Does it stay put?
No, that's the tricky part. On most conventional airfoils, the CP moves. It tends to move forward as AOA increases towards the stall and moves aft as AOA decreases.
Why does that matter?
It hugely affects the aircraft's balance and stability, the pitching moments. Designers have to account for this movement so the plane remains controllable throughout its flight envelope.
Wow. Okay, so that's lift in two dimensions. But wings have tips. What happens out there? Something about vortices.
Ah, yes, wingtip vortices. They're an unavoidable consequence of generating lift in 3 dimensions. Remember the pressure difference? High pressure below the wing, low pressure above.
Yeah.
Well, air doesn't like pressure differences. So the high pressure air under the wing tries to flow outwards around the wingtip towards the low pressure area on top.
It spills around the edge.
Exactly. This creates a rotating flow, a spiral of air trailing off each wingtip like miniature tornadoes. Left wingtip makes one spinning one way, right wingtip makes one spinning the other way.
And these vortices, they affect the lift.
They do. They induce a downward flow of air behind the wing called downwash. This downwash effectively changes the angle at which the airflow meets the wing further inboard.
So it reduces the effective angle of attack.
Locally, yes.
Yeah.
And more importantly, it bends the overall lift vector slightly rearward, that rearward component of lift. That is induced drag.
Ah, so the vortices cause a type of drag.
They are the primary cause of induced drag, which is why it's sometimes called drag due to lift. It's the energy wasted in creating those swirling vortices.
And manufacturers try to reduce this. Those little fins on the wingtips.
Winglets. Winglets are exactly for that. They act like a dam, reducing the amount of air spilling over the tip, weakening the vortex, and reducing induced drag. Tapering the wings towards the tips also helps by reducing the pressure difference near the tip. It all improves efficiency.
Okay, so we have lift pushing up, drag pulling back. Let's cover thrust, the forward push.
Thrust, the forward-acting force from the power plant. Its job is to overcome drag. If thrust is greater than drag, the aircraft accelerates.
If thrust equals drag.
Constant airspeed. If thrust is less than drag, the aircraft decelerates. Simple relationship.
But you can fly level at different speeds, right?
Yeah.
How does thrust interact with angle of attack there?
Great question. You absolutely can maintain straight and level flight over a wide range of speeds. The key is coordinating thrust and angle of attack.
How so?
At low air speeds, you need a high AOA to generate enough lift to equal weight. At high air speeds, you need a much lower AOA, sometimes even slightly negative. Now, if you increase thrust, you generally increase airspeed. More speed means more lift at the same AOA. So to stay level, the pilot has to decrease the AOA to reduce lift back down to equal weight.
So more power means pitching the nose down slightly or less nose up to stay level?
Exactly. Or less power means pitching the nose up slightly, increasing AOA to maintain lift at the lower speed. It's a constant interplay. Some very advanced aircraft can even use thrust vectoring, pointing the engine exhaust to help control pitch, but for most planes, it's AOA and power coordination.
Okay, that makes sense. Now back to drag, the resistance. We know it's friction and viscosity, but you mentioned two main types.
Yes, broadly speaking, drag is split into two categories: parasite drag and induced drag.
Parasite drag sounds like something you don't want.
Pretty much. Parasite drag is all the drag that does not contribute to generating lift. It just hinders motion, and it breaks down into three main types itself.
Okay, three types of bad drag. What's the
Yeah.
first?
Form drag. This is purely due to the shape of the aircraft and its components moving through the air. Think about pushing a flat plate through water versus a streamlined shape.
Big difference.
Huge. Landing gear, antennas, engine cowlings, even the basic shape of the fuselage and wings create form drag. Streamlining is the main way to reduce it.
Okay, form drag is shape. What's interference drag?
Interference drag happens where different airflows meet and interact, typically where surfaces intersect at sharp angles, like where the wing joins the fuselage or the struts meet the wing.
There, it gets messy there.
Exactly. The colliding airstreams create turbulence and extra drag. Designers use smooth fairings, blended covers over these junctions to smooth the airflow and reduce interference drag.
Makes sense. And the third type of parasite drag?
Skin friction drag. This goes back to the boundary layer we discussed. It's the drag caused by the actual friction of the air moving across the skin of the aircraft,
Even on a smooth surface.
even on a very smooth surface. Minimizing it involves making surfaces as smooth as possible. Flush rivets, glossy paint, keeping the aircraft clean. Any roughness increases skin friction.
So form, interference, and skin friction are all parasite drag.
Mm.
They generally increase with speed, right?
Yes, parasite drag increases significantly with speed, roughly with the square of the velocity. Double the speed, you get about 4 times the parasite drag.
Okay. Now the other main type, induced drag. You said this one is linked to lift.
Yes, induced drag is the unavoidable consequence, the price of generating lift. It's directly related to those wingtip vortices and the downwash they create.
Remind me how that works again. Vortices create downwash.
The downwash behind the wing effectively tilts the total lift vector slightly backward. That backward component of the lift force is induced drag.
Ah, okay. So it's literally a part of the lift force, just pointing the wrong way.
In effect, yes, and here's the crucial part. Induced drag is highest at low airspeeds and high angles of attack.
Why low speeds?
Because at lower speeds, you need a higher angle of attack to generate enough lift to counteract weight. Higher AOA means stronger wingtip vortices, more downwash, and therefore more induced drag.
So induced drag decreases as airspeed increases.
Exactly. It varies inversely with the square of the airspeed. This is the complete opposite of parasite drag.
So you have parasite drag going up with speed and induced drag going down with speed.
Precisely. If you plot them on a graph against airspeed, parasite drag curves upwards, induced drag curves downwards. When you add them together to get total drag, you find there's a specific airspeed where total drag is at a minimum.
And that minimum drag speed must be important.
Very important. It's the speed for maximum aerodynamic efficiency. We call it LD max, the speed where the ratio of lift to drag is highest.
LD ratio, lift divided by drag, a measure of efficiency.
Exactly. A higher LD ratio means the wing is generating more lift for each unit of drag it creates. LD max occurs at a specific angle of attack and airspeed, and it corresponds to the point of minimum total drag. Flying at this speed gives you the best glide distance and often the best endurance.
Got it. Okay, one force left. Weight. Seems simple, just gravity pulling down.
Fundamentally, yes. Weight is the combined load aircraft structure, engines, fuel, crew, passengers, cargo, all pulled towards the center of the Earth by gravity.
But where that weight acts matters, right? The center of gravity.
The center of gravity, or CG, is absolutely critical. It's the theoretical point where the entire weight of the aircraft is considered to be concentrated. Its location affects stability and controllability profoundly.
And in stable flight, lift has to equal weight.
In level unaccelerated flight, yes. If lift becomes less than weight, the aircraft starts descending. If lift becomes greater than weight, it starts climbing. It's the balance point.
Okay, so those are the four forces in equilibrium. But planes don't just fly straight and level. Let's talk about aerodynamics and maneuvers, starting with something dangerous, wake turbulence.
Right. Those wingtip vortices we discussed don't just create drag. They persist in the air long after the plane has passed, creating powerful, invisible turbulence.
And they're strongest when?
They're strongest when the generating aircraft is heavy, clean, and slow. Think large aircraft during takeoff or landing approach. They need a high angle of attack in those phases, which generates the strongest vortices.
So following a large jet too closely on approach is a bad idea.
A very bad idea. Pilots have specific procedures to avoid wake turbulence. The basic principle is to avoid flying directly through the flight path of the aircraft ahead.
How do they do that practically?
On takeoff, you aim to lift off before the rotation point of the preceding aircraft and climb above its path. On landing, you aim to stay above the preceding aircraft's glide path and touch down beyond its touchdown point. You also need to maintain separation, especially altitude separation, usually at least 1,000 feet when directly behind.
And wind affects where these vortices go.
Oh, absolutely. They drift with the wind. A light crosswind can hold the vortex right over the runway for a surprisingly long time. Pilots need to consider wind conditions carefully. And a helicopter downwash creates its own kind of turbulence, especially when hovering. Need to give them space, too.
Okay, wake turbulence is a hazard behind a plane. What about when a plane gets close to the ground itself? Ground effect.
Ground effect is fascinating. When the wing gets very close to the surface, usually within one wingspan, the ground itself interferes with the normal airflow pattern.
How does it interfere?
It restricts the downward flow of air off the wing, reducing downwash and significantly weakening those wingtip vortices.
Less downwash, weaker vortices.
Right.
That means less induced drag.
Exactly. Induced drag decreases dramatically in ground effect. And at the same angle of attack, the wing produces more lift.
So the plane becomes more efficient right near the ground.
Yes, which has big implications. On takeoff, the reduction in drag might allow the aircraft to lift off slightly below its normal takeoff speed.
Sounds good, but is it?
It can be a trap. If you lift off too early and then try to climb out of ground effect without enough speed, you suddenly encounter that increased induced drag. The plane might struggle to climb or even settle back onto the runway. Sticking to the recommended takeoff speed is vital.
And landing. That's the floating feeling, right?
That's ground effect in action. Reduced drag means the plane wants to keep flying. If you have even a little excess speed coming into the flare, you can float a long way down the runway before touching down. Pilots need to manage power carefully to counteract it.
It really is a continuous negotiation with the air. Okay, let's talk about how pilots actually control the aircraft, the axes of rotation.
Every aircraft maneuvers around 3 imaginary axes, all passing through its center of gravity. First is the longitudinal axis, running nose to tail. Rotation around this is called roll.
Controlled by the ailerons on the wings.
Correct. Second is the lateral axis, running wingtip to wingtip. Rotation around this is pitch nose up or nose down.
Controlled by the elevators on the tail.
Usually, yes. And third is the vertical axis, running top to bottom. Rotation around this is yaw nose left or right.
Controlled by the rudder on the vertical tail fin.
That's the standard setup for conventional airplanes. Other types, like weight shift trikes or powered parachutes, use different mechanisms shifting the pilot's weight or pulling on steering lines, but they're still controlling motion around these same 3 axes.
And these controls create forces that cause rotation, or moments. What exactly is a moment?
A moment is simply a rotational force. It's the force applied multiplied by its distance from the axis of rotation, or the CG in this case. Designers carefully position the CG and the control surfaces, especially the tail, to ensure the moments from lift, drag, thrust, and weight are balanced, and that the controls have enough authority to overcome them and maneuver the plane.
Pilots control the magnitude of the forces, mainly lift via AOA, and thrust via power.
Exactly. They don't change where the forces act, but they modulate them to control the aircraft's attitude and flight path. This leads directly into stability.
Aircraft stability. The tendency to return to straight and level flight after being disturbed.
That's the essence of it. It's an inherent quality of the aircraft's design. We talk about 2 types, static stability and dynamic stability.
Static is the initial reaction.
Yes. Positive static stability means if it's disturbed, it initially tends to head back towards equilibrium, like a ball in the bottom of a bowl. Neutral means it stays in the new position. Negative means it tends to move further away, like a ball balanced on top of a bowl. You definitely want positive static stability.
And dynamic stability is what happens over time. Does it settle down?
Right. Positive dynamic stability means the oscillations that occur after a disturbance get smaller and smaller until it settles back, like a well-damped pendulum. Neutral dynamic means it keeps oscillating forever. Negative dynamic means the oscillations get bigger and bigger. Again, positive dynamic stability is the goal.
And stability is different from maneuverability or controllability.
Yes. Maneuverability is how easily the aircraft can be maneuvered and how much stress it can withstand. It's about performance and strength. Controllability is how well the aircraft responds to the pilot's inputs. You can have a very stable aircraft that's not very maneuverable, or vice versa. Good design balances all three.
Okay, let's look at stability around each axis. Longitudinal stability, first pitching nose up and down.
This is stability about the lateral axis. It's crucial for preventing the nose from pitching uncontrollably. It primarily depends on the relative locations of the wing, where lift acts, the CG, where weight acts, and the horizontal tail surface, which provides a balancing or damping force.
How does the tail provide balance?
Most aircraft are designed so the CG is slightly ahead of the center of lift from the wing. This creates a natural nose-down tendency. The horizontal stabilizer is then set at an angle, often a slight negative AOA, to produce a balancing downward force at the tail.
A downward force. The tail pushes down.
Yes, strange as it sounds. This downward tail force counteracts the nose-down tendency from the wing-CG relationship, keeping the aircraft level. It also acts like a restoring force. If the nose pitches up, the AOA on the tail increases, creating more downward force, pushing the nose back down. If the nose pitches down, the tail's downward force decreases, letting the nose come back up.
It's like a self-correcting seesaw.
A good analogy. Speed and power also play a role through changes in airflow and downwash over the tail, generally reinforcing the stability. A well-designed aircraft, trimmed for level flight, will tend to return to level flight after a pitch disturbance, perhaps with a few gentle diminishing oscillations.
Okay, what about lateral stability, rolling side to side, keeping the wings level?
This is stability about the longitudinal axis. Several design features contribute. The most common is dihedral, that upward angle of the wings you see when looking head-on.
How does dihedral help?
If a wing dips, say the left wing goes down, the aircraft starts to slip sideways towards the low wing. Because of the dihedral angle, the low wing now meets the relative wind from the slip at a slightly higher angle of attack than the high wing.
So the low wing gets more lift.
Exactly. More lift on the low wing helps roll it back up towards level. It's a passive stabilizing effect. Wing sweep back also contributes a bit to lateral stability in a similar way during a side slip. And the keel effect, especially in high-wing aircraft where the fuselage hangs below the wing, uses the fuselage area like a keel to resist rolling.
Clever. Now, directional stability yawing, keeping the nose straight, like the feathers on an arrow.
Precisely like the feathers on an arrow. This is stability about the vertical axis. The biggest contributor is the vertical fin, or tail. If a gust pushes the nose sideways, the airflow hits the side of the fin,
Creating pressure.
creating pressure that pushes the tail back, realigning the nose into the relative wind. The fuselage area behind the CG also contributes to this weather vaning effect. Sweep back helps a little here too. Directional stability is usually the easiest to achieve in design.
But sometimes these stabilities interact in weird ways. You mentioned Dutch roll.
Yes, sometimes stability characteristics around different axes can couple together. Dutch roll is a classic example. It's an oscillation involving both rolling and yawing simultaneously. The nose makes a sort of figure-8 motion. It's usually dynamically stable, meaning it damps out, but it's uncomfortable and inefficient. That's why many jets have yaw dampers.
And spiral instability. That sounded worse.
Spiral instability can happen if an aircraft has strong directional stability but weak lateral stability, weak dihedral effect. A small disturbance, like a slight side slip, causes a strong yaw back into the wind, but the weak dihedral doesn't level the wings quickly enough. The outer wing speeds up, generates more lift, increasing the bank. This can lead to a gradually tightening, steepening spiral dive if the pilot doesn't intervene. It highlights why constant pilot monitoring is needed.
So the shape of the wing from above the planform also affects stability and performance.
Absolutely. Key aspects of the planform are aspect ratio, taper, and sweepback. Aspect ratio is the ratio of the wingspan to its average chord width.
Long, skinny wings versus short, stubby ones.
Right. High aspect ratio wings, like on gliders, are very efficient, producing less induced drag, especially at high AOA. Great for climbing and gliding, but they are heavier and less structurally stiff. Low aspect ratio wings are more common on high-speed aircraft.
And taper, where the wing gets narrower towards the tip.
Tapering helps reduce weight and drag and can improve lift distribution. Most wings use some degree of taper. The overall shape matters too. Elliptical wings are theoretically the most efficient for subsonic flight, minimizing induced drag, but complex to build. Rectangular wings are simple and tend to stall nicely at the root first, providing warning.
So they're good for trainers.
Very common on trainers, yes. Most modern aircraft use some form of tapered or swept planform as a compromise between efficiency, structural needs, and handling characteristics.
Okay, let's bring this back to maneuvers. How do these forces work in a turn? You said banking is key.
Absolutely essential. You don't steer an airplane with the rudder like a boat, you bank it using the ailerons. When you bank, the lift force, which always acts perpendicular to the wingspan, is tilted.
So it's not pointing straight up anymore.
Right. It now has two components: a vertical component that still opposes weight, and a horizontal component that points towards the center of the turn.
That horizontal component is what actually pulls the plane around the turn.
That's the centripetal force, yes. But notice, because lift is tilted, the vertical component is now less than the total lift. So to maintain altitude in a turn,
You need more total lift than in level flight.
correct, which means you need to increase the angle of attack, usually by pulling back slightly on the controls.
And more AOA means more induced drag.
You got it. So you usually need to add a bit of power in a turn to maintain airspeed. The steeper the bank, the more lift needed. The higher the AOA, the more drag, and the faster the rate of turn.
What about slipping and skidding turns? Bad coordination.
Yes. A slip happens if you have too much bank for your rate of turn. The plane slides downwards towards the inside of the turn. A skid is the opposite. Too much rudder, not enough bank for the rate of turn. The tail slides outwards. Both are inefficient and feel uncomfortable. Coordinated flight uses rudder to keep the tail following the nose perfectly.
And importantly, stall speed increases in a turn right because of the extra load.
Critically important. The load factor increases in a turn due to the centrifugal force. This increased load requires more lift, meaning a higher AOA for any given speed. Since stall happens at a critical AOA, you'll reach that critical AOA at a higher airspeed in a turn than in level flight. Steep turns dramatically increase stall speed.
Okay, what about climbs? How do the forces shift?
To enter a climb, you increase AOA, pull back, and usually add power. The increased lift starts the climb. Once established in a steady climb, lift will actually be slightly less than weight.
Less. How does it keep climbing?
Because thrust is now tilted upwards slightly along the flight path. A component of thrust is helping to pull the aircraft upward, making up the difference. Also, a component of weight now acts rearward along the flight path, adding to drag. That's why you need excess thrust greater than drag to climb. Your rate of climb depends on how much excess thrust you have.
And descents are the reverse.
Pretty much. You reduce AOA, push forward, and typically reduce power. Lift becomes less than weight, initiating the descent. Now, a component of weight acts forward along the flight path, effectively adding to thrust. That's why you need to reduce power to maintain a constant airspeed in a descent. It's all about reestablishing equilibrium in the new flight path.
Let's revisit stalls. You emphasized it's about exceeding the critical angle of attack, not just low speed.
Absolutely, the most critical point about stalls.
Yeah.
A stall is airflow separation from the wing surface because the AOA is too high, causing a sudden loss of lift. It always happens at the same critical AOA for a given wing configuration, regardless of airspeed, weight, load factor, or altitude.
So you can stall at high speed.
Definitely. An abrupt pull-up, even at high speed, can yank the AOA past the critical point. Turning stalls, as we discussed, happen at higher speeds due to increased load factor. Low speed is just the most common scenario where pilots inadvertently increase AOA too much, trying to maintain lift.
And planes are designed to stall predictably. Route first.
Most training aircraft are. Stalling the wing route first ensures the ailerons near the wingtips remain effective for roll control during the stall and recovery. Designs use wing twist, washout, or stall strips near the route to encourage this. Recovery usually involves reducing the AOA by lowering the nose. Aft CG makes recovery harder.
And ice. Ice is terrible for stalls.
Devastating. Even a thin layer of frost or ice roughens the wing surface, disrupting airflow and causing it to separate at a much lower angle of attack than normal. It dramatically reduces the lift coefficient and increases drag. It lowers the stalling AOA and increases the stall speed. Extremely dangerous.
Given AOA is the real trigger for stalls, AOA indicators in the cockpit sound incredibly valuable.
They're a huge safety enhancement. Loss of control in flight, LOCI, is the biggest killer in general aviation, often involving stalls. Relying only on airspeed is flawed because stall speed changes. An AOA indicator gives direct feedback on your margin above the stall, your stall margin awareness.
It shows how close you are to the edge, regardless of speed.
Exactly. It helps with energy management, situational awareness, and can even improve efficiency. The FAA strongly encourages them. They aren't foolproof. You need calibration, awareness of flap effects, icing issues, but they provide critical information airspeed alone cannot.
Okay, let's talk propellers. They're basically rotating wings, right?
That's the perfect way to think about them. Each blade is an airfoil, shaped to generate thrust, a forward-acting force by accelerating air backward.
They have camber, leading edge, trailing edge, just like a wing.
Yep. And blade angle is the angle between the blade's chord line and the plane it rotates in. Pitch is related. It's the theoretical distance it would screw forward in one revolution. There's always some slip, so the actual distance is less.
And they generate thrust through pressure differences too.
Yes, the airfoil shape creates lower pressure on the forward face, pulling it forward, combined with the dynamic pressure from deflecting air backward. They're most efficient at a small positive angle of attack, just like a wing.
Why are propeller blades twisted?
Because the tip of the blade travels much, much faster than the part near the hub. If the blade had the same angle all the way along, the tips would be stalled while the root wouldn't be doing much. The twist ensures that the angle of attack is relatively constant along the blade's length, so the whole blade works efficiently together.
Clever. And constant speed props automate the pitch adjustment.
They do. A governor automatically changes the blade angle, pitch, to maintain a constant engine RPM selected by the pilot. It allows the prop to take a big bite, low pitch, high RPM for takeoff power, and a smaller, more efficient bite, high pitch, lower OPM for cruise, like an automatic transmission optimizing efficiency.
While on props, let's tackle those left-turning tendencies. Torque and P-factor. Why does the plane want to turn left?
It's actually four distinct effects that often combine. First is torque reaction, pure Newton's third law. Engine turns the prop clockwise from the cockpit view.
So the plane wants to roll counterclockwise or left.
Exactly. Designers often build in slight engine offset or wing rigging to counteract this baseline tendency.
Okay, torque reaction, what's second?
The corkscrew effect, or spiraling slipstream. The air pushed back by the prop spirals around the fuselage. At high power and low airspeed, like takeoff, this spiral hits the left side of the vertical tail.
Pushing the tail right, yawing the nose left.
Precisely. As airspeed increases, the spiral elongates and has less effect on the tail.
Third, gyroscopic precession.
Yep, the spinning prop acts like a gyroscope. A force applied to a gyro is felt 90 degrees ahead in the direction of rotation. So in a tail dragger, when you lift the tail during the takeoff run, you're applying an upward force on the bottom of the prop disc. This results in a force acting on the right side of the prop disc.
Pushing the nose left again. Yeah.
Right. It's most noticeable in tailwheel aircraft during attitude changes.
And finally, the famous P-factor, or asymmetric loading.
P-factor is significant at high angles of attack, like in a climb. The downward moving blade on the right side has a higher effective angle of attack and velocity relative to the air than the upward moving blade on the left.
So the right side generates more thrust.
Yes, more thrust on the right side of the prop disc pulls the nose to the left. This effect diminishes as AOA decreases towards level flight.
So pilots are constantly using rudder, mainly to counteract these combined left-turning tendencies.
Constantly making small adjustments, especially during takeoff and climbs when power is high and airspeed might be relatively low, it becomes second nature.
Let's talk about load factors. G-forces. It's not just about pilot endurance, it's about the plane's structure.
Absolutely. Load factor is the ratio of total lift being generated to the aircraft's weight. In level flight, it's 1G. In a maneuver, if lift equals 3 times weight, the load factor is 3G.
And exceeding the plane's G limit is bad.
Very bad. It can overstress the structure, potentially causing immediate or cumulative damage. Aircraft are designed with limit load factors, maximum safe load, and ultimate load factors, 1.5 times limit, where failure occurs. These limits vary by aircraft category: normal, utility, acrobatic. Acrobatic planes are built much stronger.
And load factor increases rapidly in turns.
Exponentially, especially beyond 45 degrees of bank. A 60-degree level turn imposes a 2G load. An 80-degree turn is nearly 6G. Most standard category aircraft aren't designed for sustained banks that steep.
And crucially, higher load factor means higher stall speed.
Yes, stall speed increases with the square root of the load factor. If your plane stalls at 60 knots at 1G, it will stall at about 85 knots at 2G, like in that 60-degree bank. Pulling 4G means doubling your stall speed.
Wow, that leads to VA, maneuvering speed.
Design maneuvering speed, VA. It's the maximum speed at which you can apply full abrupt control deflection on one axis without exceeding the limit load factor. Below VA, the plane should stall before it brakes. Above VA, you could brake the plane before it stalls if you make sudden, large control inputs. That's why you slow down in turbulence.
So VA protects the structure, and load factors vary in other maneuvers too.
Yes. A normal stall is 1G entry, but recovery pull-ups can easily exceed that. Spins are usually low G, but recovery can be higher. Aggressive pull-ups or high-speed stalls can generate very high Gs. Smooth control inputs are key. The VG diagram graphically shows the aircraft's safe speed versus G-load envelope.
You mentioned the canyon turn example earlier, emphasizing how speed affects turn radius.
Right. Rate of turn depends on bank angle and airspeed. Radius of turn depends on the square of the airspeed and the bank angle. Doubling your speed quadruples your turn radius for the same bank angle.
So in that canyon, speeding up to try and turn tighter is exactly the wrong thing to do.
Disastrously wrong. You need to reduce speed or increase bank within limits, or both, to tighten the turn radius. Slowing down is often the safer option.
Finally, let's touch on weight and balance again. Why is it so critical?
Because it affects everything. Performance, stability, controllability, structural integrity. An overweight aircraft won't perform as expected: longer takeoffs, slower climbs, higher stall speeds, and exceeding structural limits is dangerous.
And the balance, the CG location, is just as important as the total weight.
Arguably more important for safety. A CG too far forward makes the plane nose-heavy, sluggish, requires more elevator force, and increases stall speed.
And too far aft.
That's generally more dangerous. An aft CG makes the aircraft less stable, potentially unstable. Stall recovery becomes difficult, spin recovery might be impossible. It requires less control input, which might feel nice initially, but it's closer to the edge of control. Adhering to the calculated weight and CG limits for every flight is non-negotiable. You often can't fill every seat, every bag space, and the fuel tank simultaneously and still be within limits.
Okay, we've covered a huge amount about flight below the speed of sound. What happens when planes go really fast? High-speed flight, approaching Mach 1.
Things change dramatically. At lower speeds, we treat air as incompressible. But as you get faster, closer to the speed of sound, air starts to compress, its density changes locally around the aircraft. This is compressibility.
And the air over the wing speeds up even more.
Right. So airflow over parts of the wing can actually reach supersonic speeds, Mach 1 or higher, even while the aircraft itself is still flying subsonic. This is the transonic regime, a mix of subsonic and supersonic flow over the aircraft.
And the speed of sound isn't constant.
No, it depends primarily on temperature. It's slower in colder air, so it decreases significantly with altitude. That's why we use Mach number, the ratio of true airspeed to the local speed of sound. Subsonic is below about Mach 0.75, transonic up to Mach 1.2, supersonic above that.
What's critical Mach number, Mach crit?
That's the speed of the aircraft at which airflow over some point on the aircraft first reaches Mach 1.0. It's a critical threshold.
Why critical? What happens then?
Shockwaves start to form where the flow decelerates from supersonic back to subsonic. These shockwaves cause a dramatic drag increase called drag divergence, buffet shaking, changes in aircraft trim instability, and can reduce control effectiveness.
So planes generally fly below Mach crit, or right up near it.
High subsonic jets often cruise most efficiently just below the Mach number, where drag divergence really takes off. They also have VMO, maximum operating speed in knots, and MMO, maximum operating Mach number limits, which must not be exceeded due to structural or compressibility concerns.
And at high altitude, stall speed and MMO can get close together. The coffin corner.
Yes, that's a dangerous aerodynamic pinch point. At high altitude, your indicated airspeed stall speed might be low, but due to the low air density, your true airspeed and Mach number are high. The stall speed in Mach increases with altitude, while the MMO limit might stay constant or decrease slightly. Eventually, they can converge, leaving a very narrow speed margin where you can't slow down stall risk and can't speed up MMO exceedance risk.
Wow. Even the boundary layer is affected by high speed.
Yes, it can separate more easily, especially interacting with shock waves. That's why you see vortex generators on many high-speed wings, tiny airfoils that energize the boundary layer, adding turbulence but delaying separation.
And the shock waves themselves, what are they like?
Abrupt changes in pressure, temperature, and density. A normal shock wave is perpendicular to the flow. Air passing through it slows down dramatically. Pressure and density jump up. They create significant drag.
And they cause other problems. Buffet, trim changes?
Yes. Shockwave formation and movement can cause Mach buffet, vibrations felt in the cockpit. They can also shift the center of pressure, often aft, causing a nose-down pitching moment called mock tuck, which requires pilot correction or automatic systems. T-tails help by keeping the horizontal stabilizer out of the disturbed wake from the wing's shockwaves.
Which is why many jets have swept wings,
Right.
to delay these effects.
Exactly. Sweeping the wing effectively reduces the component of airflow velocity perpendicular to the leading edge. The wing feels a slower speed, delaying the onset of Mach-crit shockwaves and drag divergence to a higher aircraft Mach number.
But swept wings have downsides too. Tip stalling.
They do have a tendency to stall near the wingtips first, especially combined with taper. Since the tips are far aft, a tip stall can cause a strong nose-up pitching moment, potentially worsening the stall. This, combined with the lack of warning buffet on a T-tail, can lead to deep stall issues, hence the need for stick shakers and pushers on some designs.
And high-speed flight controls have to be different too.
Yes, forces are much higher. Primary controls, ailerons, elevator, rudder, are usually hydraulically or electrically powered. You also see more auxiliary controls. Spoilers on top of the wing can spoil lift to act as speed brakes or supplement roll control. Leading-edge slats and flaps are critical for low-speed handling on wings designed for high speed. And large jets often use a movable horizontal stabilizer for trimming pitch changes, leaving the elevators free for maneuvering.
So from the thinness of air at altitude to the violence of a shockwave, it's an incredible range of physics to master.
It really is.
It's truly a testament to physics and engineering that we can navigate this complex dance of pressure, resistance, lift, weight, stability, and control. We make it look almost effortless, conquering the skies.
But underneath, it's a constant negotiation with these powerful, invisible forces of nature.
Absolutely. What surprised you most, thinking back through all this, about the fundamentals of flight?